Good afternoon, everyone. I'm Dakan Chia from KAIST. The title of my talk is Conductance Fluctuation and Dimensional Crossover in Hydrogenated Graphene Systems. This work was done in collaboration with Professor Ki-Joo Chung. For about last 10 years, graphene has generated tremendous interest in the scientific community. Although just graphene itself is a very interesting material, many people are trying to modify its electronic properties, such as by chemical modification, to use graphene in various purposes. Especially, hydrogenation has attracted much attention due to the metal-insulator transition. It was predicted that if graphene is fully hydrogenated, graphene turns into an insulator, so-called graphane. And soon after that, it was confirmed by the experiments that metal-insulator transition takes place in hydrogenated graphene. And some other strategies, such as patterned hydrogen adsorption on graphene, was suggested. In all these cases, the origin of the metal-insulator transition is the band gap opening, and therefore we can classify them as a band insulator. On the other hand, and more interestingly, the metal-insulator transition was also observed even at very low hydrogen concentrations. The origin of the metal-insulator transition in this case is not the band gap opening, but the localization of electronic states. When a little amount of hydrogen is randomly distributed in graphene, graphene should be treated as a disordered system with hydrogen defects. In our previous work, we have found that localized states appear at the low energy states in hydrogenated graphene. And from the fact that the conductance decays exponentially with the sample size, it is clear that the localization is induced in hydrogenated graphene. Meanwhile, the electronic transport behavior of disordered systems has been extensively studied over several decades. One of the most interesting phenomena is conductance fluctuations. And let me quote from a Nature article. So surprise is that these samples already exhibit large fluctuations in their electronic conductivity, which also vary from sample to sample. So for example, if in these hydrogenated graphene nanoribbon samples, they have the same sample size and disorder concentration. The only difference is the specific details of the disorder configuration. And as can be seen in this plot, the conductance exhibits the sample-to-sample fluctuations depending on the disorder configuration. So therefore, for the deeper understanding, their behavior must be understood in terms of the entire conductance distribution. If you focus on the localized transport regime, it is well known that the distribution function is log normal in 1D systems. As can be seen in this figure, the distribution function of log G is Gaussian. And moreover, single parameter scaling theory predicts that there is a universal relation between representative parameters. So if we see this equation, the variance is directly related to the mean value of log G. It is important to note that their behavior strongly depends on the dimensionality of the system. In 2D or 3D systems, the distribution is deviated from log normal, and different scaling relations are applied for 2D or 3D systems. So far, most studies have been focused on 2D or 3D or 1D separately, and no attempts has been made to investigate the dimensional transition behavior. So in this work, we investigate the crossover from 2D to 1D with the hydrogenated graphene system. We first study the properties of the conductance distribution in 1D and 2D systems separately, and then we consider the dimensional transition behavior from 2D to 1D with two different strategies. Our calculations are performed using type binding method. The nearest neighbor interactions between carbon-carbon and carbon-hydrogen bonds were considered, and all the parameters were fitted to the DFT band structure. And the conductance was calculated using Landauer-Buricker formalisms using the recursive Green's function method. As a first step, we examined the conductance behavior of 1D graphene nanoribbon system. Here, we considered both armchair and zigzag graphene nanoribbons, and various sample sizes and hydrogen concentrations were considered. The calculated variances are plotted as a function of the mean value of log G. Here, the individual data points are obtained by averaging more than 2,000 different configurations. We find that all the data points are well fitted to the single curve, regardless of the details of the system. In the strongly localized regime, the results are well described by the conventional 1D relation. And in the quasi-localized regime, the data points are described by the corrected equation. I'll skip the details about the correction scheme since we don't have much of a time. But important thing is that in both strongly localized and quasi-localized regime, all the data points fits to a single curve, which means that the graphene nanoribbon system is well described by the one-dimensional single parameter scaling theory. And next we turn to study the 2D hydrogenated graphene system. In this case, we deal with the L by L samples where the length and widths are same. Similar to the 1D case, the calculated variance values are drawn as a function of mean values. And our numerical results are compared with the approximate 2D relation, which is orange curve. And we find that there is a good overlap between our calculations and the curve. This indicates that the results are within the 2D single parameter scaling regime. So to conclude for a moment, we can say that the hydrogenated graphene system is well described by the single parameter scaling theory.
좀 하는 거예요?
발표 연습하는데.
발표 연습.
예.
혹시
예. 예, 알겠습니다.